Welcome back to Mechanical Engineering Made Simple.
Hey, it's great to be here again.
So I want to start today with, well, a bit of a provocative thought. Because usually, we think of engineers as the people who build things.
Right, the creators.
Exactly, the creators. But I was looking through the research for this deep dive, and I realized there's this whole other side to the job that we kind of ignore. Like, if I hand you a blueprint and a calculator, you're a designer.
Sure.
But if I hand you a flashlight and, I don't know, send you into some dark, creaking basement to figure out why a massive support beam is cracking, what are you then?
Well, at that point, you're a detective.
Right. And that is exactly the vibe I want to capture today, that detector story. We focus so much on the clean math of design, but the real deep dive happens when that math meets the messy, unpredictable reality of the physical world.
It does. When a bridge starts groaning or a machine part just snaps, it's telling you a story.
A pretty scary story, usually.
Yeah. Usually it's a tragedy, or at least it's a warning that a tragedy is coming. Structures talk to us through stress and strain, but you have to know the language to actually understand what they're saying.
So that's our mission today. We are going to perform a structural autopsy, hopefully on a patient that is still alive. We want to take you, the listener, with us on a site inspection to learn how to read this anatomy of failure.
I like that framing. And for this inspection, we're going to need a very specific toolkit because we aren't just looking at, rust or peeling paint.
Right.
We're looking for the fundamental signatures of mechanics. Things like tension, compression, shear, bending, and those really tricky instability failures like buckling.
Okay, so set the scene for us. Where exactly are we going today?
All right, imagine you're a structural engineer. You've just been called out to this old industrial site. Let's say it's an aging truss bridge.
Like one of those heavy steel lattice ones you see at a rail yard.
Exactly. Huge steel plates, thousands of rivets. It's old, and it's been carrying much heavier trucks than it was originally designed for way back when. And the site manager meets you at the gate, and he just says, the bridge is making noises, and it doesn't look straight.
Man, it doesn't look straight. It has to be the scariest sentence an engineer can ever hear.
Oh, it's right up there at the top of the list. So we put on our hard hats, we walk out onto the deck of this bridge, and we just start looking.
Where do we even start? Because my instinct would be to look at the giant beams holding the whole thing up.
That's the temptation. But the first rule of structural detection is you don't look at the main members first. You look at the connections.
The joints, why start there?
Because forces flow like water through a structure. The load of those heavy trucks has to pass from one beam to another through these tiny choke points.
I see.
So if there's going to be distress, the joints are usually the very first place to start screaming.
Okay, so I'm walking up to a connection. I see two massive steel plates, and they're overlapping, held together by this really heavy, thick bolt.
What else do you see?
Well, at first glance, it looks fine, just dirty. But looking closer, maybe the paint is cracked right in a ring around the bolt head.
Yes. Cracked paint is a really subtle clue, but it's vital. It means there has been movement relative to the steel.
So the joint is actually slipping.
Exactly.
Let's unpack the physics of that slip. If the plates are sliding, what kind of force is actually hitting that bolt? It's not pulling it apart like a tug of war.
No, a tug of war would be tension. What we're dealing with here is shear.
Shear stress.
Right. Imagine those two giant steel plates are trying to slide past each other in opposite directions, and that single bolt is the only thing standing in the way.
So it's like a pair of scissors.
Or a guillotine. The plates are literally trying to slice that bolt in half right across its diameter.
Okay, I have a good handle on the scissors visual, that makes sense. But looking at the sources we have, there's a concept here that really trips people up. Complementary shearing stress.
Yeah, that one can be tough to visualize.
It sounds way more complicated than a guillotine.
It sounds complex, but it's actually just a strict requirement of nature. Let's try to visualize it. Imagine we could shrink down and see inside the actual metal of that bolt.
Okay, we're inside the bolt.
Now, draw a tiny, perfect square on the side of the bolt material, just a little geometric square.
Got it. Visualizing the tiny square.
Now, apply that sliding guillotine force. The top of the square is getting pushed hard to the right by the top plate, and the bottom of the square is getting pushed hard to the left by the bottom plate.
Okay, so the square distorts. It's not a square anymore. It turns into a rhombus, like a slanted diamond shape.
It does. But think about the rotational force there. If I push the top to the right and the bottom to the left, what does that little square element actively want to do?
Oh, I see. It wants to spin.
Right,
It would rotate clockwise completely.
exactly. But here's the thing. The bolt isn't spinning.
Right. It's bolted down. It's a static piece of steel stuck in a hole. It's not a turbine blade.
So physics demands that for that little square to remain perfectly static, there has to be an opposing force to stop the spin.
Wait, really?
Yeah. To balance that horizontal shearing couple, the material itself automatically generates a vertical shearing couple.
Hold on. So even though the plates are only pulling horizontally, the steel creates a vertical force just to keep itself from rotating.
Yes. You physically cannot have shear on just one plane. If you have horizontal shear, you must have vertical shear of the exact same intensity.
Wow.
So that little element inside the bolt is essentially being attacked on 4 sides simultaneously just to maintain equilibrium.
That makes the environment inside that bolt sound incredibly hostile.
It is a pressure cooker of stress in there.
So back to our inspection on the bridge. I'm staring at this loose joint with the cracked paint. Did the bolt fail?
Well, there are usually 3 ways this specific crime scene plays out.
Yeah.
Scenario 1, the bolt loses the fight. The shear stress gets too high, it exceeds the material strength, and snap.
Just sliced right in half.
Cleanly in 2.
That would be a catastrophic sudden drop.
Very sudden. Scenario 2 is that the plate fails in tension instead. You have to remember, drilling a hole makes a steel plate weaker.
Because it's literally missing material where the hole is.
Exactly. So if the load gets too high, the plate just rips apart right across the line of the holes. Kind of like
It's like tearing a perforated zipper on a bag of coffee.
perfect analogy. It
Oh.
just unzips. But let's look at your joint again. The bolt is still there. The plate isn't ripped.
Right. But when I look really, really closely at it, the hole itself isn't round anymore. It's oval.
That is scenario 3, bearing failure.
Bearing failure. Walk us through that one.
In this case, the bolt was actually stronger than the plate. It didn't snap in half. Instead, it had to go almost like a plow.
A plow.
Yeah, the contact pressure between the side of the bolt and the side of the hole was so intense that the steel of the plate literally yielded. It turned into a paste and just slowed out of the way.
Oh, wow.
The bolt just crushed its way slowly through the metal, elongating that perfect circle into an oval.
That tells us a lot about the history of the bridge, doesn't it? Because
Yeah.
that's not a sudden snap.
No, not at all. Bearing failure is a progressive story. It's telling you, hey, this bridge has been overloaded for a long, long time. The steel has been physically deforming bit by bit.
Which makes the joints sloppy.
Exactly. It changes the geometry of the entire bridge.
Okay, so clue number 1 for our detective notebooks, bearing failure at the joints. The connections are sloppy and loose. So let's move on to the main members.
Where to next?
I'm looking under the roadway at the floor beams, the big horizontal beams that actually hold up the trucks as they drive across.
And what do you see?
Well, they aren't straight anymore. There's a visible sag right in the center. The beam is essentially smiling at me.
That is a smile you absolutely never want to see on a job site.
Hmm.
We are officially moving from shear into the world of bending.
Now, bending feels intuitive to me. You put heavy weight in the middle of a board, it bows down. But I really want to dig into what is happening internally to the metal. Is it just stretching?
It's actually a conflict. Bending is a dual-natured beast. Think of the steel beam like a really thick sponge.
Okay, a sponge.
When you take that sponge and bend it downwards in the middle, the top surface becomes concave. It gets shorter.
Right. The top fibers are being squashed together.
Exactly. So the top is in compression. But look at the bottom surface. It becomes convex. It's getting longer.
So the bottom fibers are being pulled apart in tension.
You got it. The beam is fighting itself. The top is violently pushing inward, and the bottom is violently pulling outward.
That implies a pretty crazy paradox, though, because if the top is getting shorter and the bottom is getting longer, just logically there has to be a layer somewhere in the exact middle that is, well, doing nothing.
The Switzerland of the beam.
Huh. Yes. The neutral zone.
We call it the neutral axis. It remains exactly its original length. Theoretically, the bending stress right there in the middle is absolutely zero.
I've always found this mind-blowing. You have this massive, heavy, incredibly strong steel beam, and the material right in the dead center is carrying almost zero bending load.
Correct. It's just sitting there. And that single realization is the reason the modern industrial world looks the way it does. It's the whole reason we have I-beams.
I actually wanted to ask about that. Why shape them like an eye? Why not just use a solid, thick rectangle of steel?
Well, think about it. If the center of the rectangle isn't doing any work in bending, why pay for that steel?
And why carry the extra weight of it?
Exactly. So engineers essentially scoop out all that lazy material. We put the bulk of the steel at the very top and the very bottom.
The flanges.
Right, the flanges, where the stress is the absolute highest.
Yeah.
And we leave just a very thin sliver of metal in the middle, the web, just to connect them together.
It turns a heavy, solid block into an I shape, which is infinitely more efficient.
It's engineering elegance.
But wait, if the middle does literally nothing, why have that thin web at all? Why not just have an empty space, like a truss does?
Oh, that's a great question. Remember the shear we just talked about, that guillotine force?
Yeah, the sliding force.
Yeah, the web handles the shear. While the big top and bottom flanges handle the bending, that thin web in the middle is what stops the top flange from just sliding right past the bottom flange.
Ah, okay. So you can't get rid of it entirely, but you can make it thin.
Precisely. But let's go back to our bridge inspection. Our I-beam is sagging, right? And it looks like it's sagging a lot.
Yeah, a really noticeable sag.
Then we have a major problem on our hands. We need to distinguish between elastic and plastic deformation.
Elastic just means it bounces back, right? Like a spring.
Yes. In elastic bending, the atoms in the steel stretch away from each other, but they don't lose their grip on each other.
So if the heavy truck drives away, the beam snaps perfectly back to straight.
Exactly. But if the weight pushes past what we call the yield point, the atoms actually let go. They slide past one another and find entirely new neighbors.
They rebond in a permanently new position.
Correct. The material stops acting like a solid spring and starts flowing almost like a super stiff fluid.
So that smile I'm seeing.
It's permanent. The beam has yielded and formed what structural engineers call a plastic hinge.
A plastic hinge? That sounds terrible. It sounds like the end of the line for the bridge.
It's the beginning of the end. It's a collapse mechanism. The beam might still technically hold the weight for now, but it has lost all its stiffness.
It's acting like an actual door hinge.
Just a rusty hinge. It's just rotating.
Yeah.
If we add even one more heavy truck to that span, it won't fight back. It'll just fold in half.
Man. Okay, so we've got oval holes at the joints. We've got plastic hinges in the floor beams. I'm honestly almost scared to look at the vertical columns now.
You should be.
Yeah.
Because the columns, the struts, that's where the most dangerous failure mode lives.
Okay, I'm walking over to one of the tall vertical steel supports. And, well, it's not crushed, it's not ovalized, but when I get right up to it and sight down the line of it, it's bowed outward, just slightly.
That is buckling. And it is the absolute silent killer of structures.
Why silent? The plastic hinge gave us a big, obvious warning sag.
Because yielding is a material failure.
Mm-hmm.
The steel itself is giving up. Buckling is totally different. Buckling is a geometric failure. It's an instability.
The sources use a soda can analogy to explain this, which I loved. Walk us through that.
It's the best way to visualize it. Take an empty aluminum soda can and stand on it gently.
Okay.
If you balance your weight perfectly straight down, it holds you easily. The aluminum cylinder has plenty of compressive strength.
It's strong enough to hold a person.
But if someone reaches down and just taps the side of the can with a pencil,
Crunch.
instant catastrophic collapse. It didn't suddenly run out of material strength, it ran out of stability.
Right.
The moment it bowed even slightly from that tap, the leverage of your weight pushed it further out, which created more leverage, which pushed it further.
It's a runaway feedback loop.
Exactly. It folds in an instant.
And the key factor here isn't just the thickness of the steel column, is it? It's the length.
Yes, that is the slenderness ratio. And the math here is entirely unforgiving. We use the Euler buckling formula. I won't recite the whole equation, but the relationship is critical.
What's the relationship?
The strength of the column drops off with the square of its length.
The square. So if I have a column that can safely hold 100 tons, and I swap it out for one that is twice as tall,
It becomes 4 times easier to buckle. It can only hold 25 tons now.
and if I make it 3 times as tall,
It's 9 times weaker.
wow, that is a massive, massive drop-off.
It is. Length is the ultimate enemy of stability.
So that slight bow I'm seeing in the bridge column,
It implies the column has reached that critical tipping point. And remember, in the real physical world, nothing is perfectly straight. We call it initial curvature.
so the bridge was probably built with some tiny millimeter imperfection.
Right. And as the loads increased over the decades, that imperfection grew. That bowed column isn't just damaged. It is a ticking time bomb.
Okay, that's terrifying. Now, so far we've covered steel, which is ductile. It stretches, it bends, it gives us some kind of warning. But what if parts of this structure are made of brittle materials, like old cast iron fittings or the massive concrete footings in the river.
Now you are opening a totally different case file, the vast difference between ductile and brittle failure.
So mild steel is ductile. It necks down. It gets really thin right before it breaks, almost like pulling a piece of warm taffy apart.
Exactly. It spends a huge amount of energy just trying to stay together. But brittle materials, your cast irons, concrete, glass, they don't stretch at all. They just snap.
And the sources mention something genuinely fascinating about how they snap. The chalk experiment. This really made the physics click for me.
Oh, this is a classic engineering classroom demo. Take a regular piece of blackboard chalk. Chalk is incredibly brittle. Now grab the ends and twist it. Apply pure torsion.
Now, my intuition says if I twist it, it should just snap straight across the middle, right? Or maybe splinter down the length of it.
But it doesn't do either. It breaks in a spiral. It forms this absolutely perfect 45-degree helical fracture.
But why 45 degrees if I'm twisting it in a circle? Why is it breaking on a slant?
This brings us all the way back to that idea of forces transforming inside the material. We call it principal stresses.
Okay.
When you twist a shaft, you think you're just applying shear stress. But that twisting motion internally creates tension, a literal pulling force, acting at a 45-degree angle to the axis of the shaft.
Wait, so just by twisting it, I'm creating a stretching force inside.
Yes, and brittle materials absolutely hate tension. Concrete and cast iron are fantastic at being squashed in compression, but they are terrible at being pulled apart.
So the chalk just gives up.
It fails exactly perpendicular to that invisible pulling force, hence the 45-degree crack.
That is wild. So if I'm inspecting our bridge and I see a 45-degree crack in a cast iron support bracket,
It immediately tells you that member was being twisted. It wasn't being crushed, it was being torqued. The crack literally draws a visual map of the forces that caused it.
it's like the material leaves a fingerprint for the detective.
Even steel does this, actually. There's a visual phenomenon called Luder's lines.
Luder's lines.
Yeah, when mild steel just barely starts to yield, you can sometimes see these faint 45-degree crosshatch patterns magically appear right on the surface of the metal.
Almost like stretch marks on the steel.
That's exactly what they are. It's the internal crystal structure physically slipping along the planes of maximum shear stress.
Incredible.
So if you see those lines on a steel plate on your bridge, you know yielding has begun, even if absolutely nothing is broken yet.
Okay, so we've diagnosed the patient thoroughly. We've got bearing failure in the loose joints. We've got plastic hinges forming in the beams, buckling in the tall columns, and helical cracks in the brittle fittings.
It's a mess.
But here's the real problem for us as the engineers fixing it. This bridge has thousands of rivets. It has hundreds of interconnected beams.
Right, and everything is linked together. If you go in and just reinforce that one buckling column, you make it much stiffer.
Which means it'll attract more of the load.
Exactly. And that extra load might cause the weak floor beam right next to it to finally snap.
It's this massive, complex ecosystem of forces. We can't possibly calculate all of those cascading effects by hand.
Not in a single lifetime. And this is exactly why modern structural engineering relies on something called the finite element method, or
Sure.
FEM.
I hear FEM thrown around a lot in the industry. I know it involves running computer models and looking at those really colorful heat maps. But what is the software actually doing? Is it just a basic physics simulation?
Think of it as digitizing the physical structure. We can't solve the calculus for a continuous, highly complex shape like a whole bridge. It's mathematically impossible. So we chop the bridge up.
Into elements.
Exactly. Millions of tiny triangles, cubes, and rectangles. We essentially turn the bridge into a massive digital mesh of Legos.
And why does making it out of digital Legos make the math easier?
Because we know the physics of a single, tiny, simple shape perfectly. We can write a very simple equation for how one single cube squishes or stretches based on its material. We call that its stiffness matrix.
Ah, so you just have millions of tiny, simple equations for millions of tiny cubes.
And then the computer matrix solver crunches them all simultaneously. It figures out how pushing on cube A affects cube B, which then pushes on cube C.
It tracks the movement of every single connection point.
Every node, yes. So when you see those colorful simulations on a screen, the bright red for danger zones, the cool blue for low-stress tree, that is the direct result of the computer solving millions of little spring equations.
So it lets us do structural surgery with a scalpel instead of a sledgehammer. We can see exactly where the stress bottlenecks are and weld a reinforcement plate only on that one specific area.
Exactly. It turned engineering from this dark art of estimation into a game of extreme precision.
Amazing. Well, I want to wrap up today's deep dive by opening up the engineer's handbook, so to speak. We've covered the heavy inspection stuff, but there are some fundamental concepts in the source material that I see people get wrong online all the time.
Oh yeah, lots of misconceptions out there.
And these misunderstandings actually lead to some of these catastrophic failures. Let's do a quick FAQ to close out the case file.
Let's clear them up. Hit me.
First one. This is the heavy hitter. Stress versus strain. People use these words totally interchangeably in casual conversation, like, I'm under a lot of stress or I'm straining to lift this.
Yeah, but in physics, they are cause and effect. That is the absolute best way to remember it. Stress is the load divided by the area. It is the internal pressure. It's the push.
And strain.
Strain is the response to that push. Strain is the physical deformation. It's the percentage change in the length of the material. Stress is how hard you pull it. Strain is how much it actually stretches.
So you could have really high stress, but very low strain.
Absolutely, like pulling on a diamond. Or you could have low stress with massive strain, like lightly pulling on a rubber band.
Got it. Which leads perfectly into the second big confusion point, stiffness versus strength.
A massive, massive difference. Strength is the finish line. It's how much ultimate load it takes to actually break the material in half.
Okay.
Stiffness, on the other hand, is the journey to that finish line. It's how much the material resists bending or stretching along the way.
So using the rubber band again.
A rubber band has very low stiffness. It stretches incredibly easily, but it actually has decent strength. It takes quite a bit of stretching to finally snap it relative to its size.
And what about glass?
Glass has very high stiffness. It fiercely resists bending, but it has relatively low tensile strength. It shatters easily once you hit its limit.
Yeah.
They have designed for both.
Right, because if I have a steel floor beam that is strong enough to never break, but it bends 3 inches every time you walk across it.
It's strong, but it's not stiff enough. And people will be absolutely terrified to walk on it because it feels like a trampoline.
Exactly. Okay, third question. Why do things break when they are below their calculated limit? Like, we did the math, we found the yield point, we stayed well under it, and the part still snapped.
That is the ghost in the machine. Fatigue.
That paperclip effect.
Exactly. Take a normal metal paper clip, bend it open once, it's fine, bend back closed, still fine. Do that 20 times, snap.
Even though you never pushed any harder than you did on the very first bend.
Right. But the cycle, the back and forth repetition, it woke up microscopic cracks inside the metal structure.
And then just slowly grow.
They grow a tiny fraction of a millimeter with every single cycle, until the remaining solid metal is just too small to hold the normal load. And then sudden unexpected failure.
That is what kills bridges that have seen too many traffic cycles over the decades.
Yes. The steel remembers every single truck that ever drove over it.
That is genuinely haunting. All right, last one for the FAQ. The factor of safety. Is this just engineers being overly cautious or unsure of their own math?
I like to call it engineering humility.
Humility.
Yeah. Look, we can calculate the bridge load as 10 tons. We can calculate the steel's braking strength as exactly 50 tons. But we know reality is incredibly messy.
Trucks are illegally overloaded. The steel gets rusty. A massive wind gust hits at the worst time.
Exactly. The factor of safety is just the numerical gap between the yield stress where it breaks and the working stress, which is what we allow day to day. We designed the bridge to hold 3 times the expected load, not because we want to waste the client's money.
But because we're buying insurance against the unknown.
Precisely. We know the math model is not reality.
I love that. It's acknowledging that the map is definitely not the territory.
Always.
Well, we've walked the bridge today. We've seen the ovalized holes of bearing failure, the terrifying smile of the sagging beam, and the silent bow of that buckling column.
And we've seen how the math, from just simple algebra all the way up to complex Fem matrices, is the primary tool we use to stop it all from collapsing.
It really changes how you look at the physical world. You just don't see static, boring buildings anymore. You see all these invisible forces constantly fighting to get to the ground.
You see energy.
Yeah.
And that's actually the final thought I want to leave everyone with today, the concept of hidden energy.
Explain that a bit.
When you stretch a rubber band, or when a heavy truck bends a huge steel beam, work is being done. You are physically pumping energy into that material, and it gets stored right there in the atomic bonds.
We call that strain energy, right?
Yes.
Yeah.
It's potential energy, just waiting. A standing bridge isn't just a dead pile of steel and concrete. It is a massive, highly charged battery of stored energy.
Wow.
Structural failure is simply that stored energy finally finding an escape route.
And usually finding a very violent, explosive escape route.
Right. Our entire job as engineers is just to manage that energy,
Wow.
to design safe channels for it to reach the ground so it never has to release itself violently.
That is such a powerful image. We aren't just stacking bricks and bolting steel. We are literally containing lightning.
In a manner of speaking, yeah, we are.
Well, consider my perspective totally shifted. That's it for this deep dive inspection. If you want to see what a plastic hinge or those Luder's lines actually look like in real life, or if you want to understand the exact math behind that stiffness matrix we talked about.
Which is fascinating to see mapped out visually, by the way.
It really is. So if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.
See you next time.